Let's say we've got 3 people. Person A, you know what, let's call it John, okay? Okay, person A, John, has a mass of, let's say 70 kilograms. 1 meter, 1.0 meter to John's right is another person that we're going to call Spencer. Spencer's mass is going to be, let's say 50 kilograms. I have no idea, by the way, what people's mass is. I'm making those up. Let's say 0.50 meters to the right of Spencer, this isn't drawn to scale, obviously, is another person that we're going to call Jeff. Actually, let's not call it Jeff because we're going to get confused with John here. Let's call it Luis. Third person to the right, Luis. We're going to make his mass. Luis, what's your mass? We're going to make you 60 kilograms. It's been a bit generous. Don't think you're quite 60 kilograms, but that's okay. We want to find the force of gravity caused by John and Luis on Spencer. In other words, who's attracted to Spencer more, John or Luis? Well, we know they both produce a force of gravity on Spencer. Both of those forces are really, really small because the masses of John and Luis are really, really small. Now, Luis has a smaller mass than John, so you'd think he should produce a smaller force, right? But Luis is closer. So who's going to produce the bigger force? I don't know. John should produce a bigger force because of his mass. Luis should produce a bigger force because of his proximity, 0.5 meters. Who produces the bigger force? What does the net force become on Spencer? Here's what we got to do first. Draw the free body diagram. Going back to free body diagrams, we did that with inclined plane problems and pulley problems and vertical circular motion problems that we did a few days ago. Now we're doing it with gravity problems. John pulls Spencer to the left. We're going to call that Fj, the force of John to the left. Does that make sense? Now, Spencer pulls John to the right, right? Okay. Spencer's attracted to John. John's attracted to Spencer. There's going to be a force on John to the right. But I'm not going to draw that in because I'm not trying to find the force on John. Okay, I'm trying to find the force on Spencer. So let's just draw the force on Spencer. The force of John on Spencer is to the left. What about Luis on Spencer? Well, Spencer is pulled to the right as a result of Luis. Now, Luis is pulled to the left, but we don't really care. No offense, Luis. We don't really care what happens to Luis here because that's not the question. We're trying to find the force on Spencer. So draw all the forces acting on Spencer. It's like saying, look, a tow truck is pulling a car down the road. What's the net force on the car? We draw a free body diagram for the car, not the tow truck. Okay, draw the free body diagram for the object you're trying to find the force on, which in this case is Spencer. Now, look, you get the free body diagram drawn. Let's calculate both of those forces. Fj, the force of John on Spencer, is going to be gm1m2 over r squared. That's 6.67 times 10 to the minus 11 times m1, mass of, what did we use here for mass 1, John or Spencer? Or does it matter? Right? Doesn't matter. Doesn't matter. The distance here, this one's easy because we got 1 meter, right? Let's figure that out. 6.67 times 10 to the minus 11 times 70 times 50 divided by 1. The answer is 2.3345 times 10 to the minus 7 newtons. 2.3345 times 10 to the minus 7 newtons. All right, are we done? No. We know the force of attraction between John and Spencer right now, which is pretty weak, by the way, actually. John's not all that attracted to Spencer after all, apparently. 10 to the negative 7 newtons. Let's find the force of Luis on Spencer now. force of Louis on Spencer is gm1 m2 over r squared. 6.67 times 10 to the minus 11 times the mass of 50 or 60. What do I use? Doesn't matter. It doesn't matter who's m1 and who's m2. 50 times 60. The distance this time is 0.50 meters. Let's figure out what that force is now. I get 8.004 times 10 to the minus 7 newtons. Who attracts Spencer more? Louis or John? Louis does. Louis is lighter, 20 kilograms lighter. How can he attract Spencer more? Because he's closer to her. Okay, proximity. Sorry, John. There's other fish in the sea, John. Don't worry. Now, we're not quite done, because the point of this wasn't so much to find the force that each of them exert on Spencer. The point of it was to find the net force on Spencer, the overall force of gravity on Spencer. So now what are we going to do as a last final step in order to determine the net force on Spencer? Yeah, we're going to add the two, but we're going to add one of them as a negative value. So in effect, it's the same thing as subtract them, right? We're going to say the net force, as we always do, the net force is equal to the sum of the forces. In this case, Fj plus Fl. Well, Fj here is, what is that, 2.3345 times 10 to the negative 7 newtons plus 8.004 times 10 to the minus 7. Is that right? I mean, it's not right, is it? Close. What am I missing? Yeah, missing that negative sign in front of the 2.33. That's why I drew the free body diagram, to tell me that the first one, Fj, should be a negative value. Let's add those up and let's see what we get. We get 5.6695, 5.7 times 10 to the minus 7 newtons. Spencer's got all these guys around her attracted to her. They're all pulling her in every which direction. The problem is, it kind of cancels a little bit, eh? It reduces the overall attraction when all these guys are attracted to her. The net force of attraction is 5.7 times 10 to the minus 7 newtons. That makes sense? Listen, we haven't done this question per se before, but we really have. We've drawn free body diagrams a million times before. We've said F net is equal to the sum of the forces a million times before. We've added those forces together, as Liam said, paying attention to the negative sign right there in front of ones that are to the left, making the ones that are to the right positive. We've done that a million times before. We've done F is equal to gm1 m2 over r squared. Not a million times before, because that was just the other day. But we've done it before, right? It's not all that hard. All we're doing here is combining a few things together. What we did a couple of days ago, gm1 m2 over r squared, the law of gravitation, along with this whole deal about net force and free body diagrams. You guys feel okay there? Okay, let's throw an example question at you, or a practice problem, I should say, at you. Okay, let's take a look at practice problem number 1 on page 209. Let me give you some data for the Earth, the Moon, and the Sun, because that comes from the example that's actually in your textbook that we decided not to use. Okay, give you some data from that, and then I want you to try to tackle question number 1 on page 209. If you feel like a bit of a challenge, if you feel like you're really smart, you don't have to be nearly as bright as you did to answer that question that I gave you, that challenge question with the guy, the pulley on the inclined plane with the elevator and the projectile motion, not anywhere close to that. But if you feel like you could be a little bit challenged here, like this is maybe a little bit too easy, give question number 2 a try as well. Okay, we have to be able to do number 1. Okay, if you can do number 2, that'd be great. It's not quite as critical as number 1 though. If 1 is okay, let's have a look at number 2. This one's a more challenging question, I think. During the first quarter phase of the moon, Earth, the moon, and the sun are positioned as shown in 4.22. Calculate the net force of gravity exerted by both the moon and the sun on the Earth. Well, the first thing we got to do, because there's more than one force acting on the Earth, is draw a free body diagram. The force of the moon on the Earth, force of the sun on the Earth, I should say, FSE, the force of the sun on the Earth, is to the right. The sun pulls the Earth to the right. Now, the Earth pulls the sun to the left, but I don't really care because I'm not trying to find the force on the sun. It's just like when we were talking about the force of gravity between Spencer and John, we didn't really care what the force on John was. Even though there was one there, we didn't care about it because we were trying to find the force on Spencer. The world revolves around Spencer, right? We're trying to find the force on her. Now, the force of the moon on the Earth is upwards. The force pulls the moon to the, the force of the moon pulls the Earth upwards towards it. Okay, I'm going to call it FSE, the force of the sun on the Earth, and FME, the force of the moon on the Earth. There's also a force that's equal and opposite on the moon, but I don't care about that because I'm not trying to find the force on the moon. I'm trying to find the force on the Earth. So let's get both of those forces. The force of the sun on the Earth is G M1 M2 over R squared. Okay, that's 6.67 times 10 to the minus 11 times the mass of the Earth, which is 7.35 times 10 to the 22, times the mass of the moon. No, it's not. It's 5. Okay, that's the mass of the moon. The mass of the Earth is 5.97 times 10 to the 24. Let's divide that by the distance between the moon and the Earth, 3.84 times 10 to the 8. And let's square that. What do we end up getting there for the force of the sun on the Earth? 3.53 times 10 to the 22. All right, so the force of the sun on the Earth, pretty big. 3.53 times 10 to the 22. You would expect it to be pretty big because this force is what keeps the Earth in orbit around the sun. Listen, if the Earth is going to stay in orbit around the sun because of this force, it's going to be a big force. Why? The Earth is big. It takes a lot of force to keep it from moving off in a straight line. Now, we're not done, though. Let's find the force of the moon on the Earth. It's G times M1 times M2 over R squared. We get 6.67 times 10 to the minus 11 again. The force of the moon, or the mass of the moon, I should say, is, wait a second, what have I done there? What have I just calculated? What did I calculate up top there? There's a mistake there, I think. William? Yeah, I just calculated the force of the moon on the Earth, right? I used all the data for the moon. Okay, that's okay because I needed that. But that means that down here, I'm not going to calculate the force of the moon on the Earth. That means down here, I'm going to calculate the force of the sun on the Earth. Doesn't matter what order you do it in. I'm sorry? What's the wrong value? What is? Oh, okay, okay. I see what you mean. So what does this work out to be then? 1.99 times 10 to the 20. Is that right, guys? Okay, thank you. All right. That's a smaller force than we had, which makes sense. We thought we were calculating the force of the sun on the Earth. Now we're calculating the mass of the moon on the Earth. Well, would you expect the force that keeps the moon in orbit around the Earth to be bigger or smaller than the force that keeps the sun in orbit around the Earth? Or the Earth in orbit around the sun, I should say. The moon is going to be smaller, right? It's a lot lighter. The force keeping it in orbit doesn't have to be nearly as big as the force acting on the Earth to keep it in orbit. Okay, this is going to be the mass of the sun. What was that, 1.99 times 10 to the 30? The mass of the Earth is 5.97 times 10 to the 24. Divided by the distance between the sun and the Earth is 1.50 times 10 to the 11. Square it. And Dustin, what do we get for that? 22? 3.53 times 10 to the 22 newtons. Now, this is where a few people that came up to ask me questions as you were working on this had some trouble. We get both of those forces. That's great. How do we combine them? Draw a diagram. Not a free body diagram. We already have that. Let's draw a vector diagram. The force of the sun on the Earth is 3.53 times 10 to the 22 newtons. The force of the moon on the Earth is upwards, and it's 1.99 times 10 to the 20 newtons. Let's combine them. Let's combine them. There's my net force right there. We find that net force by doing the Pythagorean theorem. And we find the angle by doing the inverse tan function of opposite over adjacent. The force should work out to be 3.52 times 10 to the 22. And the angle should work out to be 0.3 degrees. Good. All right, I'm not sure how many of you have noticed this, but when we were using that equation the last couple of days for Newton's law of universal gravitation, F is equal to gm1 m2 over r squared, there was a constant in there, a number in there that I just told you the value of. Big G was 6.67 times 10 to the minus 27. 6.67 times 10 to the minus 11, I should say. That's a small number. And it's a number that's always the same no matter where we go in the universe. Where did this number come from, though? Where do we get this number? Where did Newton get this number from when he derived his law of universal gravitation? Well, the simple answer to that is nowhere. He didn't. Newton didn't get this number. Newton knew what the equation was that described the force of gravity that acts between two objects, but he didn't know what the constant would be. He knew that there needed to be a constant. He knew that there needed to be a value there in this equation. He just didn't know what that constant should be. So Cavendish comes along a little bit later and performs an experiment to determine the value of G. And this is what Cavendish did in his experiment. Essentially, it's a bit of a simplification, but essentially, he's got a string attached to the ceiling. That string has a rod attached to the end of it with a mass here that we call M1, with another mass right here that's nothing. We're just balancing M1 so the thing doesn't tip over. We're going to bring another mass nearby that we're going to call M2. It's my fist. As I bring my fist nearby it. As I bring my fist nearby mass 2, bring nearby mass 1, what happens to mass 1? There's going to be an ever so slight force of attraction between the two. Mass 1 will be pulled towards mass 2. Now, how many of you all should raise your hand to this. I'm sure you've all done it before. How many of you have ever sat on a swing set and twisted that swing set around as far as you could and then let it go so you'd start swinging back, start rotating back, spinning back, right? You guys have all done that, right? You guys know intuitively the more you twist that swing set, the more force it's going to take, right? The harder it is. As you twist it a little bit, it's easy. As you twist it more and more, it becomes more and more difficult, right? You guys ever notice that? Yeah, the torsional properties of that swing, that chain, or the twisting properties of that chain dictate that the more it twists, the bigger the force is required. You could, if you wanted to, you could go out there, do an experiment on the swing set, and determine how much force is required when it made 1 revolution. Well, if you wanted to twist it 3 revolutions, how much force would be required? You wanted to twist it 5 revolutions, how much force would be required? You could measure that. You could record that. And you could get a table of values that told you when it twisted this much, there must have been this much force applied to it. That's what Cavendish would have done. He would have brought mass 2 nearby mass 1. This string would have twisted as a result of that, just like your swing set does. He could have measured the value of the force of attraction simply by seeing how much the string twisted. Just like you could figure out how much force you applied on that swing set simply by looking at how much the swing set twisted, the torsional properties of the swing set. Now, you could easily measure the value of mass 1 and easily measure the value of mass 2. You could also easily measure the value of r, the distance that separates m1 and m2. Look, if you've got m1, m2, r, and f, let's get back to Newton's equation for a sec. K q1 q2 over r squared. You got this variable, you got this one, you got this one, you got this one. The only thing we don't have here is k. Solve it. Solve for it. F times r squared. R squared comes up by multiplying over q1 times q2. If you can find f and r and q, then plug them in and solve for k. When we do that, we end up getting that value for k of 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. Is that okay? The Cavendish torsion balance experiment, or the Ryan swing twisting experiment. Think of Ryan or somebody on a swing twisting this thing around. He can measure the force. He can measure the distance from somebody else. He can measure the mass of him and that somebody else. Put all those together, we can calculate the value of g, that constant that we want to find. Right? So the number that I gave you a couple of days ago for the gravitational constant, it's not just from nowhere. It comes from somewhere. It's a number that isn't just made up. It comes from an experiment that's used to determine it. Okay. Here's a little bit of homework for you. Page 215, question number 1 to 6. You might have a couple of minutes at the end of class to work on that, but you don't right now. Okay? Just write that down right now, page 215, number 1 to 6. And if we don't get to it today, then just take a peek at it for homework tonight. We're going to move on now. We're getting close, actually, to the end of the unit here. Gravitational fields. We talked about gravitational forces. What's a field? Well, let me ask you this question. I've got a board marker in my hand right now. How would we figure out the force of gravity acting on this board marker? There's two ways here. What's the force of gravity acting on this board marker? What's one of the ways to find it? This is not a hard question. Okay, mass times 9.81. So the force of gravity acting on the board marker is the mass of the board marker times 9.81 meters per second squared. Good, thank you. That's one of the ways. What's the other way of finding the force of gravity acting on the board marker caused by the Earth? We've just done it the last couple of days. What is it? Joe? Right, good. F is equal to g m1 m2 over r squared. Now, does it really matter which of those equations I use to find the force of gravity acting on this pen? Not really. Not really. Why did we even use that second equation, by the way? Why did we even introduce that a couple of days ago? Why couldn't we always just use F is equal to m times g? Here's the problem. We don't always know what g is. Right here, it's about 9.81. If you go up into space and you happen to be, when you're, 10, 15 years from now, when you're a little bit older and you're an astronaut, and you go up and spend 6 months on the International Space Station, g is not going to be 9.81. What's its value going to be? We don't know exactly, but it's a little bit less than 9.81. You can't find the force of gravity acting on you by using m times g unless you know the value of g. And g changes. This equation, the second one, is a little bit more versatile because we don't need to know what little g is. We don't need to know whether it's 9.81 or 9.76. Does that make sense? Nevertheless, okay, on the surface of the Earth or near the surface of the Earth, they'll both give you the same result for the force of gravity acting on this pen. This pen experiences the force of gravity caused by the Earth. What if I take the pen away? Okay, there's the spot right now where the pen was. What's the force of gravity now at that spot? The pen's not there anymore, right? It's gone. What's the force of gravity at that spot now? Zero. There is none, right? You can't have a force if there's nothing there to experience the force. What's a force defined as? Push or pull. So we define a force as a push or a pull. If you don't have anything to push and you don't have anything to pull, then you don't have a force. Got it? Well, that's miraculous. I just took the pen away and gravity disappeared? Oh, of course not. We talked about the curvature of space-time the other day. When I take that marble away from the corner of the blanket in that fabric of space-time, does the curvature of that blanket go away? No, it was caused by the rock in the middle, right? It was caused by whatever was heavy making the curvature of space-time, making the gravitational field. Gravity doesn't disappear, right? If I take this pen away, gravity's still there. It just isn't doing anything. To help us to understand that gravity is still there, even when there's nothing to experience it, we talk about a gravitational field. Okay, field versus a force. A field is that influence that's there no matter what, as long as we have the producer. The force is the push or the pull acting on the pen or whatever it is. In general, we define a field as a line of influence that surrounds something. And a gravitational field, of course, is a line of influence that surrounds a mass. It shows us the influence of the mass that produces gravity, even if there's no board marker there to experience it. It shows us that the influence of gravity is still there. To have that field, all we need to have is the producer. In this case, the example that I was just giving you, all we need to have is the Earth. The pen doesn't need to be there. Now, the pen could be there. The gravitational field will still be there, but we don't need to have the pen there. As opposed to a force, though, the push or a pull, where you do need the pen to be there. So a force describes more the effect on something, the effect on the pen in the gravitational field. The field itself describes more the cause, in a sense. The Earth's gravitational field is there because the cause is there. Doesn't matter if there's anything there to feel it or not. Now, of course, as we usually do, we'll talk about vector scalar gravitational field. It's what we call a vector field because there is a direction associated with that influence. If I put this pen, this board marker, in the gravitational field about a meter above the surface of the Earth, it's influenced by the gravitational field. In which direction? Which direction is this pen influenced? If I let this pen go, what way does gravity take it? Good. Down, right? Of course. There will never be a time when gravity pulls this pen upward. Never. The gravitational field is a vector field. It influences this pen and every other object, for that matter, in a very specific direction. Because of that, we call it the vector field. All masses will experience a force in the direction of that field. Whether it be a pen or there be you. We all experience a force in the direction of the field. In the direction of the field, the vector field. Once you get that copy down, we're going to leave it there for today. There are a couple equations that help us to describe mathematically these vector fields, these gravitational vector fields. But we'll go those tomorrow because we don't quite have time to do it today. Okay, get this copy down, then take a look at those 6 questions for homework if you wish, or just work on them at home tonight. Make sure you have those 6 questions done, though, and we'll take a peek at those tomorrow. That's it.